Hello everyone and welcome to lecture 4 of Data 102. This lecture is going to have two parts. In the first part, we're going to cover the online false discovery rate problem. And we're going to do this with a few recorded videos from Professor Mike Jordan. So in these videos, we're going to introduce what the problem is, and then followed by an algorithm, the so-called LOT algorithm that helps to solve this problem. This segment ends with two videos describing a heuristic proof of the algorithm. And in this semester, we're going to make those two videos optional. So this is not so much to downplay the importance of the online FDR problem or the LOT algorithm. It's simply that the math that goes into this proof is a little bit tricky. And although it's kind of rewarding to understand the proof, we don't want you to sweat it too much if you don't really understand the details. Instead, the most important takeaway from this segment is first, an appreciation of what the online FDR problem is, how it's different from the original FDR problem that we told you in the previous lecture, and also an intuitive understanding of how the LOT algorithm works. In the second part of this lecture, we're going to cover ROC codes. ROC codes are a really important topic in data science, and they're used everywhere, both in science and industry. On the other hand, they are also surprisingly subtle. And in this lecture, we want to try to give you an appreciation for some of the nuances of this topic. Now, if you do a Google search, you'll be able to find many fantastic videos about ROC curves. You don't really want to compete with these videos. So instead, we're going to do things a little bit different. So we're going to use a Jupyter Notebook and walk through a real data set and see how we can try to motivate and develop ROC codes to try to understand it. Okay, so that's it for the summary of today's lecture. We hope that you enjoy it.
Okay, so let me introduce the online problem, and then I'm going to take a couple of minutes break. I may or may not get all the way through this, which is okay, because I want you to, this is a part that I really want you to focus on and understand in this class. It's going to be a really cool algorithm. And so let me set it up, and then we'll take a little bit of a pause. All right, so the online problem, what does online mean? Online means that we don't wait till the end of gathering a lot of data and make some analysis. We do it during the gathering of the data. And maybe the gathering of the data goes on forever. It's a stream of data. And we'd like to find an algorithm that works on the stream of data. In essence, you can stop me anytime and ask, how am I doing? And I say, I'm doing fine. And you can look at my error rates, and they're always under control. This is kind of what you really want for a scientist or a piece of technology, right? Is to solve the online problem. And this is really not a classical problem. It was really not studied hardly at all. It's a very much more recent problem. It's kind of now at the research frontier. But again, the point of this class is in many cases to bring research frontier ideas into the undergraduate curriculum, because I'm pretty convinced that you guys can understand it and use it. Okay, so how could we develop FDR control that you can stop me at any moment in time and say, how many discoveries have you made up until now in your life? And I'll say, like 35. And you say, well, what fraction of those are actually real discoveries? And I can say more than 95%. I can guarantee you that. And you can stop me at any time later, the next day, or even later in my life, and it's always going to be the case. Can we do that? So here's kind of a pictorial representation of this. The classical procedure gathers together like a bag of p-values or something that makes the decisions on the bag. We had to sort them, right? So we had to get the whole bag. We want to get procedures where you don't have to do the sorting, where you can just keep doing them one at a time. All right, is this possible? Well, first of all, is this a reasonable thing to ask to do? Well, yeah, because this is very, very common in large-scale enterprises like, Amazon or Google or whatever. They're trying to figure out, for example, how to do a web page. Should I put a certain color in my widget? Should I choose a certain size, orientation, style, logo, and so on? Many, many of these things. And so what I'm going to do on all of those in these industries is I'm going to do an actual statistical test, so-called A/B test. I'm going to bring in 10,000 people during the day, and I'm going to give them one of the colors, and then another 10,000 people randomly chosen will get a different color, and I will see who stays on the website longer for things like that. And if there's a big difference between the two colors, I will record that and say I've made a discovery. I should use the blue color instead of the gray color. And you don't want to have a huge number of false discoveries here. That would cost you money and be painful in various ways. Now, if I took p-values for all these tests, which I can do in some generality, and I compared all of them to an alpha, what would I set alpha to? Well, if I set it just to 0.05, like in Neyman Pearson, I'm sunk. That's going to be like my problem I talked about earlier, where I had a terrible FDP. All right, so maybe I could do Bonferroni. Well, but Bonferroni says take the total number of tests and divide by that. And first of all, it's very conservative. You're not going to maybe make any discoveries. But even worse, maybe you don't know how many tests you're going to have here in this streaming setting. It could be going on forever. It could be an infinite number of tests. Bonferroni, an infinite number of tests would give you, 0 as your threshold. So is this possible to solve it at all? All right, so it's not clear how to adjust Benyamini-Hochberg and batch procedures. Bonferroni doesn't work here because, we'd set alpha to, 0.05 or the number of tests. I call it N here instead of M. But and after N tests have gone by, we're still good. But now what do we do on the next test, the N plus first test? All right, so eventually we're stuck. We just have to stop. We can't do any more tests. All right, I'm going to be using economics kind of thinking here a little bit. And so we're going to call this notion of having an alpha value of like 0.05, some wealth that you have. And you're going to use your wealth in little increments to make tests, all right? And you don't want to use up your wealth too fast. You want to invest it for the future. There's kind of a whole economics metaphor here. And let me just say, in my own research recently, I'm doing a lot of bring economics thinking into statistics and into machine learning. And this is kind of one instance of where this is happening. All right, so if we have wealth, it's kind of natural to think about, you can have increments of wealth that aren't just always the same. So we can have an alpha 1 for the first test, an alpha 2 for the second test, and so on and so forth. We could have different alpha values, so we're not stuck with just kind of one fixed value like in Bonferroni or Neyman Pearson. All right. Moreover, we could have the alphas maybe kind of decreasing kind of fast. So we could always have a little bit of wealth left over, right? They don't just kind of add up to 1 and then we're done after M tests. So I could do like alpha of t is equal to 2 to the minus t, and that could, that sums, that never gets to be bigger than 1, right? And so I could just keep going for a while. The problem here is that eventually the alphas get really, really tiny, and I have to have a really, really, really small p-value to make a discovery. So this is not seeming like it's working either. All right, so you might sort of say we're sunk here. And really, this is interesting that it took sort of some decades for people to realize that you're not sunk here. There's actually a way out of this. All right, so here's the basic idea. It's actually not going to be that hard. There's a glimmer of hope, which is that this FDP quantity that I've really insisted upon, this column-wise quantity, it's a ratio of 2 counts, okay? There's a false positive in the numerator, and then there's the total number of discoveries in the denominator. Both of those are random variables, right? After I've got some data, the amount of discoveries I will make is random, and maybe it's determined by some algorithm, and the false discoveries I make is random. So both the numerator and the denominator are random here. That's not the case in the classical testing paradigm in Neyman Pearson, right? If you were in a certain row, then you have a certain number of true hypotheses. And if you're in the other row, it's 1 minus that, or n minus that. The number of true hypotheses is fixed, right? It's not random. It doesn't depend on the data. Whereas the number of discoveries you make depends on the data. And so it's random. So we have a ratio of 2 quantities that are both random. And you can make a ratio small in 2 ways. You can make the numerator small, or you can make the denominator big. And that's what I was suggesting earlier. If we can somehow make the denominator big while not also increasing the numerator, if we can make more discoveries, that can make this overall ratio small. And it sort of shows we're a good statistician, so we should be able to continue to make more tests. All right, so the numerator has the false positive rate in it, okay? Remember, it was just the probability of false positives times pi naught divided by the probability of d is equal to 1, okay? All right, so we're still back in this problem of controlling these kind of sums of alpha values, these sums of probabilities of false positives, all right? In the batch situation, we kind of got around that by taking the whole big batch of all the alpha values and doing this algorithm with the sorting and all that. All right, here we're going to do this streaming paradigm where we're going to look at the alphas one after another, and we're going to have a different way to approach controlling these sums of alpha values. Okay, and then if we can sort of figure out a different way, but an easy way to get control of the numerator, then we can also try to make this overall quantity small by making the denominator big. And the way we can do that is hopefully make lots of discoveries. All right, and the idea is going to basically be that whenever you make a discovery, I sort of say, good statistician, I will give you a little bit of extra alpha now, and you shouldn't use it all in the next test, but you should invest it and use it for future tests and invest it wisely. Okay, that's what we'll be doing. So here's a picture. This slide, by the way, comes from Tiana Zernich, who's one of my PhD students here, and she's one of the sort of 10 people in the world who's worked on false discovery, online false discovery rate control, and has some nice papers on it. So Tiana was a GSI last year in this class and helped with this slide and a lot of the work, a lot of the homeworks. So the picture is going to basically, we start with a certain amount of alpha wealth, particularly at the beginning of your life. You're born, you're starting to be a statistician on the second day of your life, and I give you 0.05 of alpha wealth. All right, you can start to use this to test p-values and make decisions in your life. Right? Do I want the milk or do I want the skim milk or whatever? Now you make a rejection. You don't make a rejection. You accept the null. In other words, you don't make a discovery. Fine. And now you reduce your budget a little bit for the next test. Okay. And you keep doing this until eventually you make a discovery. And when you make a discovery, I'm going to give you some more wealth back. I'll give you another dose of alpha, and that'll add to whatever still residual alpha you had left over from before. And now you'll use the total that you have, and you'll start to compare that to future p-values. You'll allocate some of your alpha to the next test and the next test and the next test. And you'll kind of do this for a while in the future. And hopefully at some point you'll make another discovery, and I'll give you a little bit more alpha wealth. You'll put that in the bank, and you'll continue to decay these things over time. Okay, it's like interest of some kind. You're going to take these things, you're going to save them away in a savings account, and then the interest, you'll kind of use that to make you're going to make tests for a while. All right. Okay, so this is going to be an infinite process. This is going to keep on going. Your alpha level in the bank is going to wax and wane. It's going to go up and go down. All right, so this is really important. Statistics hasn't really had this, and also sort of computer science, that there's kind of a notion that you do something and you're done. And here, instead, we're going to try to quantify wealth. We're going to try to trade that off against other forms of wealth and so on. And this field is really, as time goes on, more and more about trade-offs. All right, so a little history. The first online FDR algorithm that I know about, at least, it was called alpha investing. It was due to Foster and Stein at Penn. And they were both in a business school and a stat department, I think. And so they kind of had this econ for spirit, and they wrote this nice paper on alpha investing. It was a somewhat complicated algorithm, and I don't want to explain it to you, and because there's a better approach to it. The one I'm going to explain to you is a more recent and simpler one called LORD. It's due to Javadmard and Montanari. It's about 3 or 4 years old, I think, at this point. We have another one called Saffron here at Berkeley that several of us have worked on, including Tiana Zernich. And it's comparable, but I want to present LORD. I think it's kind of an easier one to present. I'm not going to be able to show the proof for LORD. Okay, and so the basic idea of this algorithm is an online FDR algorithm. It's going to make tests in a sequence, and every time you make a discovery, it's going to give you a little bit of wealth, and then that wealth is going to decay. All right, and the current wealth is going to be the sum of all the decayed values from the past. Okay, so all the investments you made in the past keep adding up, and you have a total wealth at any given time that you are able to use, hopefully in a smart way for the future. Okay, now I've written down the entire algorithm here, and I don't want to we're going to have a simplified version of this algorithm, but I just copied this out of the paper because I want you to see the whole bloody thing. And I'm going to probably spend the rest of my time here just explaining this algorithm. I'm not going to go through the proof, even though it's like 3 more pages. I want to take my time. And if you want to go through it yourself offline in advance of the class, that would be great. But I will go through it at the beginning of next class. All right, so let's just go through this pseudocode slowly here. And I'm going to do a simplified version of this as we go. These folks made it a little bit more general than we really need. So what we have in the beginning, the input to this procedure is, first of all, a total FDR level alpha. So it might be 0.1. I want your overall control over a big bag of tests. You have less than, say, 10% false discoveries. We also need to define a non-increasing sequence gamma of t. Now, this is one of these sequences that decays, and it sums up to nothing to 1. So 2 to the minus t would be a perfectly fine thing to do here. If we were only doing kind of one test and we never made any discoveries, this might be a reasonable thing to do. You just kind of keep making smaller and smaller, alphas going into the future, and you kind of run out of ammunition at some point, and that's kind of fine. This gives you, if you were having no new wealth given to you, you would just do this. So gamma of t is just some sequence that sums up to 1, and 2 to the minus t is a perfectly reasonable one. But we could talk about other ways you would be able to set gamma if you chose to. All right. Then there was a notion of an initial wealth, which was gamma 0, and it needs to be less than or equal to alpha. But I'm just going to set that equal to alpha for our thinking and for my description of these algorithms. I'm going to set gamma your initial wealth just equal to alpha. Okay. All right. Now I'm going to set alpha 1 as your first little kind of testing alpha, and I'm going to make it to be gamma 1, which is maybe, in the case of gamma being 2 to the minus t, this would be a half. So I might be taking half of your initial wealth and apply that to the first test. And I'm either going to now accept or reject on the test, and then we're going to do something. Okay, so now we can start going, we enter the loop. So from t equals 1, 2, up to infinity, what we're going to do is we get the next p-value. We're going to make a new decision today. We got some new data, maybe new coronavirus data has arrived, and we're going to make a decision for this person. Okay, so we get a p-value. And remember, if p-values are small, we're going to reject, and we're going to tell somebody, yeah, you got the coronavirus. Sorry about that. So if pt is less than or equal to alpha t, so alpha t is this value that we keep updating in this kind of smart way that allows you to decide whether to reject or accept the next person in your line. So if someone's p-value is small, you'll reject, otherwise you will accept. Okay. All right. Now this next line is all, of course, where all the complication happens and all the work gets done. Now I told you that I'm going to set W naught equal to alpha. And that means that second term just vanishes. Alpha equals W naught, therefore alpha minus W naught 0. That whole second term just vanishes. So ignore that. Moreover, the first term is just gamma t plus 1 times alpha, because W naught is equal to alpha. So that first term is just a further decay of the initial value of alpha. Okay, so gamma of t plus 1 would be 2 to the minus t, right? So it'd be a quarter, an eighth, a 16th. It's just taking that initial value, decaying it forward into time. So the second one's gone, the first one's not even that interesting. It's really that sum there, which is where the action's happening. All right. And what this is it's a little convolution. If you know some signal processing, this will be very, very familiar. First of all, that bold 1 is called an indicator function. An indicator function with the brackets there is a little function that's 1 if the inequality inside the brackets is true and 0 otherwise. Okay? So if I have a 1 or a 0 inside of a sum, this is just picking out some of the terms in the sum to add in and ignoring others. It's just a kind of switch that allows you to keep some and ignore others. So what we're going to do is we're going to keep all of the cases where we made a discovery in the past. Tj, or tau j, is the time of the jth discovery or jth rejection. Okay? So I wrote that out mathematically on the last line there. You can stare at that if you want, but just in English, tau j is the time that you made the jth discovery. So maybe that's in the past. I'm going to add up with that indicator function all of the past discoveries. Okay? Every time I'm discovering the past, I'm going to include that in my sum. And then I'm going to take the gamma value, all right, of t plus 1 minus tau. All right, so if tau is way back in the past, then I have a gamma of a large number, like gamma of 20 or gamma of 40 or whatever. And gamma is a decreasing sequence. All right, so I got a smaller and smaller weight value as I go further and further back in the past. So this is just a way of adding up all of the things that come from the past, all right? And each of those things in that sum is weighted by an alpha value. So you take an alpha value from the past, it decays forward in time, and then at time t, you add up all those past values that have decayed from the initial alpha value. And so if one of them happened like 4 time steps ago, it's been decayed by a value of 1/4. If one happened 16, it's to a power. So if one happened 3 steps ago, it's decayed by 1/8. If it happened 4 steps ago, it's decayed by 1/16, and so on. So it's just adding up all the past decayed values. All right. Now the algorithm we're going to analyze next time doesn't actually, it's a simplified version of that. It doesn't look at all the past values of discoveries. It just looks at the most recent one. So it's a simplified algorithm we can actually get a proof for. The original paper does a proof for this more complicated one. but you're going to be seeing one for this simplified algorithm. Okay, so hopefully that gives you a flavor of now of a different algorithm that's trying to do something like this FDR thing. It's just giving you an alpha value that you're using to test PTs. But it's not sorting the PTs, it's not doing a threshold in that way. It's just one at a time looking at a p-value and comparing it to an alpha value. And then it adjusts the alpha value for the next test. It just keeps going forward in the future into time like that. And then we have a super intelligent little way to give you this alpha value update, this weight. And that weight goes up and down over time, allowing you to make more and more future tests. And what we need to prove is that no matter when I stop you, the total false discovery rate you have will be always less than alpha under this procedure. And that's my proof for next time. All right, so now we're finally into new material for this lecture. And this is actually not new at all. This is a review of something you should have learned in your earlier classes. This is a really important theorem from probability theory. In some ways, this is the most important theorem from probability theory for usage outside of probability theory, and maybe even inside. It's just really important. Okay, so it's kind of falls very directly from the definition of a conditional expectation. And it takes a while. It takes sort of years to kind of really get comfortable with the notion of a conditional expectation in full generality, and then to really understand this theorem and prove it in full generality. It takes a while. All right, but I really think you hopefully have already understood it, and you can work a little harder and understand it. You will all, as usual, you'll see a pretty good Wikipedia page about this if you want to have a nice little self-contained reading. All right, anyway, the theorem says that the expected value of some random variable x is equal to the expected value of the expected value of x given some other random variable y. Okay? If x and y are independent, then the inner expectation there would just be expected value of x, and that's just a number. The outer expectation wouldn't do anything, and obviously be vacuous. But it's more interesting when x and y are related, and they can be related in any way. Okay. Now, the way I think about this is that in English is that what this theorem is saying is that the average of an average is an average. Okay. The right-hand side is the average of an average. The expectation of x given y, that's an average of x for a particular region of the sample space where y is a constant. Okay. That's kind of a pretty good, not entirely, fully rigorous way to think about it, but it's pretty good. Is that in the sample space where these random variables x and y are defined, for any given value of y, there's some region that maps into that value of y. Okay, it's the region of the sample space where y is equal to some number, like 5 or whatever. Okay, and if you remember your probability theory, the way you think about this is you go backwards. You say, okay, y is equal to 5, go backwards into the sample space. What's the region that gives me y equals 5? So that's some region in the sample space. And now what I'm going to do is take an average of x over that region. Okay, that's what the expected value of x is for that particular y. All right, and so in that entire region now, x was varying in that region of the sample space. I'm going to replace x with its average over that region. So maybe the average is 4.25 in this whole big region where y was equal to 5. And so now I'm going to build a new random variable which has the value 4.25 in that entire region. And I'm going to do that for every region in the sample space where y is some constant. So I take all the values that y can take on, I map backwards, I average x over that region, and I replace x with its expected value in that region. So now I kind of have like a step function. It's kind of a function that gives you lots of averages for regions where y is constant. All right. So that's what e of x given y is. It's a random variable, e of x given y. Why? Well, because it's a function on the sample space. It's kind of a step function on the sample space. Any function on the sample space is a random variable by definition. So given that it's a function on the sample space, i.e. a random variable, I can take its expectation. All right. And the values it takes on are those kind of flat values in those regions. And so all the outer expectation is doing is averaging those values and weighting them appropriately. Okay. Weighting them according to the marginal probability of x. So the outer expectation there is a weighted average of all the averages inside. So that's the average of an average on the right-hand side. And the theorem says that gives you as if you had averaged over x from the beginning. Okay, so if you want the average over some complicated random variable x, you can do it in 2 stages. You can first do it for each value of y. Maybe that's an easier calculation. And then you can average the averages. Okay, hopefully that will help you. hopefully again, because it's recorded. If you didn't quite get it, you can listen again, and you can spend some time with me.
I have a question.
Yeah, sure.
Sorry, you probably can't see me because I'm in the dark room. But um, if we're talking about the random variable y and x, the average of x over given y, what if y is like is is only in a small range, and x exists in other, you know, in other places outside of y? Like,
No,
isn't that?
this has nothing to do with the values of x and y overlapping in some sense. Nothing whatsoever, right? All it is it says take a value of y, your favorite value of y, 5. Right? Let's suppose that y can take on the value 5, and let's suppose that x goes between 0 and 1, for example. I don't know, whatever. Okay. All right. Now, what values in the sample space give you that value y equals 5? Well, there's going to be some parts of the sample space that give you that because y can take on that value. So we usually call these omega. These are points in the sample space, all right, where y takes on the value 5. There's a whole bunch of them usually. There's maybe a whole region, all right? And now we look at all those points in the sample space, and it says, oh, for those, what value does x take on? Well, x is going to take on different values for all those points where y is equal to 5. And they're all numbers between 0 and 1. So maybe they're like, 0.3, 0.2, whatever. They're fluctuating around over over that region where y is equal to 5. Okay. And so all I do is I take an average of all those fluctuating values of x, and I'll get some number like, 0.4. Okay. For that value of y. So in the sample space now I have a region where I've said the average of x in that region is equal to, 0.4. Right? And now I do that for some other value of y, maybe 10 or whatever. And so y can take on whatever values it takes on. I just take each one of them, I go back into the sample space, and I average the x values, which are completely unrelated, over that region. And now I've got my E of x given y. Is that helping? All right, he's in the dark, so maybe that also hurts his audio somehow. Okay, hopefully that was helpful. All right, so now we're going to try to give this proof about why does this thing, control the FDR. It's actually not going to be quite the FDR. It's going to be something called the modified FDR. And I'm doing that again just to slightly simplify here so we don't focus on just a lot of math, just to get one core argument here. All right. Okay, so remember what the FDP is. The FDP is the false discovery proportion. The FDR is the expectation over that. Okay, and I'm gonna we're gonna consider the following estimate, which is an estimate of the FDP. All right, so the numerator is just the first term is the sum over I equal 1 to t of alpha I. All right. That's just an upper bound on the probability of false positives in the first t trials. Okay, why? Well, false positives are when the null is true. Okay, what's your probability of making a discovery? I.e., getting a false positive. Well, because the null is true, we know that we have uniform distributions, and if you're using alpha I as your criterion for the ith test, okay, then your probability is alpha I. And we just sum those up over the first t trials to get the total probability, the upper bound on the total probability of making a false positive on the first t trials. All right. Then we multiply by pi naught. And again, I'm ignoring that because I'm going to upper bound it with 1. Okay. And then downstairs, we don't have any approximation at all. This is literally just the total number of discoveries, right? Because it's the indicator function that a p-value was less than alpha I. Well, when a p-value is less than alpha I, that's a discovery. We make a discovery in that case. And we take the indicator of that, we get a 1 in those cases and a 0 otherwise. And if we sum these up from 1 to t, well, that's just the total number of discoveries. So there's just a mathy way of writing out the total number of discoveries in the denominator. And the numerator, we're just upper bounding our false positives with, the fact that uniform distribution, and then upper bounding the pi naught. Okay, so hopefully at this point, that's really not troubling to you. Okay, that literally is, that's going to be our estimator, and it's kind of coming right out of that kind of Bayesian equation. Okay, so now we'll do our little mathematical analysis. So The hard part here is going to be that some I equal 1 to t of alpha I. How do we get a kind of bound on that? What is happening with these alpha i's? All right, well, remember the algorithm. The algorithm starts off with an alpha value of just alpha, and then it starts to decay it. It takes alpha times a half, then alpha times a quarter, all right? And just keeps going down until you have a rejection. When you have a rejection, I give you another dose of alpha. And then that decays. Alpha goes to alpha over 2, alpha over 4, and so on and so forth, okay? So we have this kind of sawtooth kind of thing that starts up, goes up to alpha and then decays down. And then whenever you have a discovery, it goes up again, add alpha to wherever you were, and then decay down, and then sawtooth up. So every time you make a discovery, you're going to go up, and then you're going to decay away. That's the lowered algorithm in this simplified version. All right, so if we think about that sequence, sum over I equals 1 to t of alpha I, we're adding up over this sawtooth expression, okay? A decaying part, and then a new alpha value, and then a decaying part, then a new alpha value, all right? And so we can break that sum up into episodes, which are just the decaying parts, okay? Starting it up at alpha and then decaying away. Think of that as an episode. All right, and we're going to try to upper bound the sum over alpha I by breaking it into these episodes. Okay, so now in each one of those episodes, I just have a decaying sequence. All right, it starts at alpha, and then it goes to alpha over 2, alpha over 4, alpha over 8, or sorry. So I just wrote that out mathy. I said alpha times the sum I equals 1 to, the length of this episode, let's call that t prime, of gamma of wherever you started, I, plus 1 minus tau, just goes back to the most recent rejection. And so this is just the sequence 1, 1/2, 1/4, 1/8, and so on, okay? Because as t goes further, as I goes further along, you're subtracting off tau, which is staying fixed back in the past. And you're just kind of indexing further and further along and getting the bigger values of gamma. So, 1/2, 1/4, 1/8, and so on. Just that's what that sum is doing. All right. Now we can upper bound that sum by just letting tau go to t prime go all the way to infinity. Okay, we'll certainly get an upper bound because we're adding yet more gammas into our little sawtooth here. The sawtooth actually stopped at some point. We had our next discovery. All right, but we can upper bound that sum by just letting it go all the way to infinity. Why can we do, why is that reasonable? Well, if we go all the way to infinity, when we sum the gamma i's all the way up to infinity, we get something upper bounded by 1. All right, so I can get rid of all that complications there and just replace this whole thing of alpha times 1. It's an upper bound. It's rigorous. Okay, so each one of these little episodes is actually giving me a contribution of alpha times 1. All right, so now all I got to do is ask, how many episodes do I have up till time t? How many episodes do I have up until time t? Each episode is giving me a contribution of alpha to that sum of the alpha i's. The alpha i's are the decaying thing, and alpha is just that fixed number you started with. All right, so I got alpha times the number of episodes. Well, remember what the denominator is. It's the sum, it's the number of decisions, and that is exactly the same as the number of episodes. All right, the number of episodes is the number of times that you had a p-value less than alpha I. That means you had a rejection. That means you start a new episode. Okay, so the denominator is the same as the number of rejections, same as the number of discoveries. It's the same as the number of sawtooths or the number of episodes. All right, so in the numerator, we have the number of episodes times alpha. In the denominator, we have the number of episodes. It cancels, and this whole thing is less than or equal to alpha. So we just proved that FDP hat is less than or equal to alpha. Okay, and we did it just by breaking up the numerator into episodes, finding out the number of episodes is exactly the same as the denominator. That cancels, and each episode gives us a contribution at most alpha, because we have a decaying sequence that adds up to at most 1. And so FDP hat is less than or equal to alpha. All right, and we're not taking expected values here, like in the FDR, and worrying about that at this point. We'll do that on the next slide. So this is totally rigorous. All right, so it's kind of a little hard to go through proof sometimes, sometimes people just immediately get it, sometimes they're not getting it at all, and you'll have to look back at it again. But all the ingredients are here. And it really is just kind of draw yourself this little sawtooth that is given by the Lord algorithm, which is alpha, starts at alpha, then decays, then goes back up, add a new alpha, decay that away. That's what the algorithm does. Okay, so we proved that FDP hat, this quantity that we think of as an estimator of FDP hat, it's defined that way. We're thinking of it as this estimator, but it's just a definition. We prove that that sum over alpha I over the thing in the denominator, that is less than or equal to alpha. We're giving it a name. All right, so finally we're going to finish this proof on this page here. Okay, so now we're going to have to write out the FDR in mathematics. We haven't done that quite yet, I don't think so. We call it the expectation of the FDP. All right, and here's that expectation. All right, in the denominator we have the same thing we had before. It's just the sum of the number of discoveries, because whenever a p-value is less than alpha, you have a discovery. And I just used that same kind of mathematical notation in the numerator. I said, sum all the tests up to time t of the indicator pi is less than or equal to alpha I, otherwise I made a discovery, but only do that for the cases where I is a null hypothesis. In other words, this is the sum over the number of false positives. And that's exactly what the FDP is. Sum over the number of false positives divided by, it's the number of false positives divided by the number of discoveries. That is the definition of the FDP there in the brackets, now written out with a little bit of mathematical rigor. And then the FDR is just the expected value of that. And this expectation here, we're going to talk about that a little bit more, but this is a frequentist expectation. This is an expectation over doing this whole procedure again and again and again. Getting a whole brand new data set and running this whole procedure again, and then doing it again and doing it again. That's what that expectation is. It's a frequentist expectation. All right. That'll become a little more clear as we go, but just for now, think of it as just, it's some kind of an expectation of a random variable. All right, now here's the part where we're going to sort of simplify our lives. Okay, so the FDR, as you can see at the top of the page, is the expected value of a ratio. All right, and the real analysis here that goes on in these papers that we're referring to here really analyzes the FDR. It's a little more challenging, and there's a simpler analysis for something called the modified FDR. And the modified FDR just applies the expectation to the numerator separately and the denominator. All right, so you can think about this as an ad hoc, approximation if you want. You can actually prove that these things are close under certain conditions. And you can also even argue that this modified FDR is also quite a reasonable thing to ask for in certain kinds of problems. So I'm not going to go through all those arguments. It would take a long time, and I don't really want to. Just for now, just sort of trust me that this is not an unreasonable thing to study on its own merits, and it's reasonably close enough to the FDR for us to go ahead and proceed and make a proof for this, and then I'll refer you to papers if you want to see for the actual FDR. All right, so here's our final page of the proof. All right, so the first thing we do is we make this FDR approximation, okay? So we're just gonna say, okay, I should have just said MFDR is equal to, because that's actually what's happening here. Okay, so we're using this expectations, ratio of expectations instead of the expectation of the ratios. Okay, so here's the whole proof, the remaining parts of the proof. We already did a little part of the proof. All right, so what we're gonna do is compute the numerator. All right, so it's the expectation of that sum over all the i's up until time t, but just for the null hypotheses, of the indicator that a p-value is less than alpha I. Okay, now think about what's random here. Okay, when you're taking an expectation, you gotta think about what's random here. Well, the p-values are certainly random because they depend on the data. Okay, so p-values are random variables and we know what distribution they have, blah, blah, blah. The alpha values are actually random here too, because they're being defined by the algorithm, and the algorithm is responsive to the data. So these alphas are not just fixed once and for all. So in our classical work in statistics, the alphas are usually fixed, 0.05 or some decaying sequence or the Bonferroni or whatever, and that's not the case here. The alpha i's are coming out from an algorithm. So we have to make our analysis respect that. We have to be good mathematicians. Yeah, okay, so how do we do that? All right, so the first step is that I just brought the expectation inside of the sum. That you can do completely generally. Expectation of the sum is the sum of the expectation. And now inside the expectation, I used my Tower property of conditional expectation. This is what you always do when you have expectations. You think of some condition you can do to make the problem easier. I think of this as divide and conquer. Okay, you divided the problem up into a bunch of separate, simpler conditional expectations, and you put them back together with your final averaging. Divide and conquer. Okay, so what are we going to introduce as our conditioning variable? Well, we have two variables, the p's and the alphas. So one of them has got to be the conditioning variable. Let's make it be the alpha value. So I say conditional on alpha, that's like the y back in my previous slide. And then the indicator that p is less than alpha, that's like the x. So I say, okay, that overall expectation of the indicator is the expectation of the indicator given alpha I. Okay, so that's just your tower property being used here. All right, now why do I do this? Well, now that I've conditioned on alpha I, inside of that innermost expectation, I can treat alpha I as a constant. Okay, I can do the averaging with alpha I held constant. That's what conditioning is. All right, the next step is something hopefully you'll remember, that the expectation of an indicator is the same as the probability of the event. Why is that? Well, an indicator random variable takes on the value either 1 or 0. And remember what an expectation is. It's the value times the probability of that value, and you add it up over all the values. Well, if you have a value that can only take on a 0 or 1, in the case where it's a 0, I take 0 times the probability, I get 0. So it's just 1 times the probability being a 1. Okay, and the probability of being a 1 for this variable is the probability that the event happens pi less than or equal to alpha I. Okay, so I turn that innermost expectation of an indicator into a probability now. That's what that script p is. It's a probability under this same random, the same expectation of the probability that that the p value is less than alpha I. And again, everything is done conditionally on alpha I. All right, now the next step is one you should also know how to do, because the probability that pi is less than or equal to alpha I when alpha I is held fixed, okay? All right, and we're in the case of a null hypothesis, that's what our sum is here. That's just equal to alpha I. That's the uniform property of the p-values. All right, so that whole thing simplifies just to expected value of alpha I. All right. Next step, I pull the expectation outside of the sum. I can always do that. Usually this, I've moved it inside, I did some mathematical work, I did some divide and conquer, and now I'm going to put everything back together. I pull the expectation outside. And moreover, I'm going to get an upper bound here because I'm going to go ahead and sum over all of the i's, not just over the null ones. I needed the null so I could get that uniform property working for me. Now that I've done that, let's go ahead and sum over everything, because most of the hypotheses are going to be null in our situation we're interested in. All right, so let's simplify our lives by getting that expectation. All right, now what we do is we use the theorem we proved on the previous page, which is that the sum over alpha I of the sum over the indicators is less than or equal to alpha. Okay, look at what we have on the in this last equation here, right? I have the sum expectation of the sum alpha i's. Okay, if I take the very last, the FDP hat thing there, and I move the denominator over to the right-hand side, I get sum of the alpha i's is less than or equal to alpha times the sum of the indicators. If I take expectation on both sides, I get what I've got there on the line just above that. Expectation of the sum of the alpha i's, that's the numerator, is less than or equal to alpha times the expectation of the denominator, which I've now moved over to the right-hand side. Okay. All right. And now I'm done, because if I now plug this result back into that thing at the very top of the page there, I have that the numerator, the expectation of the null guys, is less than or equal to alpha times the denominator. The denominator will cancel, and I'll just have alpha. So FDR is less than, or modified FDR is less than or equal to alpha. That's rigorous. And it's approximately the FDR, but pretty good approximation at this point.
Hey, Professor, I have a quick question.
Please.
So for the expectation of the probability that pi is less than or equal to alpha I given alpha I,
yeah,
why does that equal to the summation of expected value of alpha I? So like, how do you put that probability into alpha?
Notice that the expectation didn't change. So it's not about that expectation. That's present in both parts of that. So it must be about the inside of the brackets.
Right.
Now the inside of the brackets up above there is probability that pi is less than or equal to alpha I given alpha I. So now you're licensed to think of alpha I as just a constant, you know, like 0.03 or something. It's just a constant. Right. Now, what's the probability that a p-value is less than some, you know, 0.03? Well, it's 0.03. All right, because that's the uniform distribution. The p-values have a uniform distribution. So the probability that pi is less than alpha I is just equal to alpha I. That's what the uniform distribution is. So I can take that whole complicated probability expression and just replace it with alpha I. That's all I've done.
Got it. And another one is that how does the last inequality come about? So I understand that the sum of expected value is less than or equal to expected value of summation of all t's because like I previously have a condition that it has to be I null, but then if we include all i's, the first inequality I understand, but the second one, like, can you explain that?
Yeah, the second one is that where I just use the FDP hat thing down below. That's what I'm doing now. So let me, I'll say it again slowly. So forget the FDP hat thing. That's just a name to give it to. That's just the definition. The key is that the sum of the alpha i's divided by that sum of the indicators is less than or equal to alpha. You good with me there?
Right. Mm-hmm.
Okay. Now, take that denominator. There's no expectations in this formula, right? It's just some random variable. Take that denominator and move it to the right-hand side. So now I've got on the left-hand side sum of the alpha i's, right? Less than or equal to alpha times the sum of the indicators. You with me still?
Mm-hmm.
Okay. Yes. Now take an expectation on both sides of that equation. So now I have expected value of the alpha, the sum of the alpha i's is less than or equal to alpha times the expectation of the sum of the indicators, right?
Mm-hmm.
That's what you have right above. That's the inequality you were asking about.
I see. But what is the point of having that inequality? Like,
okay, now when I have that inequality, forget all the steps that led to this result. Go back to the first part, which was when I said, and then compute. I have now the expectation of that complicated thing with the nulls and everything is less than or equal to alpha times expectation of that sum of indicators, right? That's just forget all the intermediate steps.
Okay.
And now I go back to the very top of the page, FDR, you know, approximately equal to. Well, the left-hand side of the thing I just proved there is the numerator. So I can plug in less than or equal to alpha time, you know, less than or equal to the end of this sequence of things, alpha times expectation of indicators. And now the expectation of the indicators is the same in the numerator and denominator of that FDR, and it cancels. And all I'm left with is an alpha. Did I lose you there?
So is so based on the your computation, it should be like if we divide the expectation over the, like if we look at like FDR, it should be less than or equal to alpha, right?
Yes, that's what this is showing.
I see. Okay.
This is showing. It's showing that the modified FDR, that ratio of expectation at the top of the page, is less than or equal to alpha. That's what's being, I put together the pieces there.
Thank you.
Okay. All right. So this is getting pretty close to the kind of proofs you will, you know, do. And if you really take this field seriously, you know, you'll learn how to do this kind of proof. It's really just some expectation calculations and just kind of being clear on what are the objects you're talking about here. You know, the mathematics is not that hard, you know, but it takes some time to absorb. But I just wanted to show you this is the kind of mathematics we do. Oh, I should have put that up there. That helps.
Professor?
Yeah.
For the very last inequality where you say that we're taking like FDB of t and then we're moving the denominator to the right-hand side, you said that you're then taking the expectation of both sides.
Yeah.
I was wondering why that inequality still holds when you take the expectation.
That's called monotonicity of expectations. All right. When I take a random variable being less than or equal to another random variable, then the expectation of the random variable is less than or equal to the alpha, less than or equal to the expectation of the other random variable. Okay, so this is actually kind of interesting. It's a statement about the ratio of two random variables, saying that that ratio is less than or equal to alpha, no matter what values the random variables take on. Okay, so that's actually kind of interesting.
Okay, thank you.
Yeah.
In this video, we are going to motivate and describe ROC curves, which are a tool for evaluating binary classifiers. So we saw ROC curves very briefly in lecture, but because they are so powerful and commonly used a tool, we decided that we're going to have a much longer video talking about it. Okay, and we're going to make use of Jupyter Notebook to make this video into sort of more hands-on in some way. And throughout this video, we're going to be working with this data set that you can find in sklearn. So this is the breast cancer data set. Except that I'm going to make a bunch of changes to make it slightly more interesting. Okay, so if you see what's happening here, I'm going to load the data. I extract the X and Y components of the data. But then I'm going to change the labels a little bit by flipping some of the labels at random. Okay, so in code, I'm taking the logical XOR between the original label and this sequence of Bernoulli random variables with probability p is equal to 0.8. And this means that I'm flipping the label with 0.8 probability. Okay, and the point of this is to introduce some additional noise into the data. All right, so let's run this cell. And as usual, I'm going to do a randomized split of the data into a train set and a test set. Now, if you're doing a real data analysis, it's always very helpful and pretty important to take a look at the data first. So you want to know the provenance of the data and what all the features mean, right? And you can always do this by, for sklearn data sets using this component of the data set. Okay, but we're not going to go into that today because our focus is on ROC curves instead. All right, so as a data scientist, what would you do? At this point, assuming that you've cleaned on the data, you know what you're looking for, then you will fit the model. Okay, so let's fit two different models. Let's fit a logistic regression as well as a random forest classifier. And this cell is just doing that. So it's fitting the two models and is also recording what the predictions are for every sample in the test set. Okay, so you fit your model. What do you want to do now? We want to know how well the model is doing. And actually, we want to evaluate the performance of the model in two ways, or rather for two purposes. So for the first purpose, we want to know how well the model is doing, absolutely, right? So we want to know whether we can trust the model. And then in addition to that, sometimes we have many models and we want to compare them and we want to know which model is better. Okay, and these two are not necessarily the same thing, right? So imagine that you have some score that is very noisy. You can use that to compare between models, but at the same time, you want to be able to know based on some number whether or not you can trust some model, right? And you see in some time that ROC curves is going to give you a tool to do both of these. All right. So let's try to evaluate our models. Okay, so in machine learning, the main approach to do this is to come up with some loss function and compute the loss function for your model on the test sets. And yeah, that works. And it is probably, for regression, this is definitely the first thing that you do. For binary classification, on the other hand, sometimes you want to be a bit more subtle as well, right? And as we learned in the first few lectures, we want to care about quantities like true positive rate, false positive rate, so on and so forth. So let's go ahead and compute this confusion matrix. Okay, so what's a confusion matrix? This is exactly the 2x2 table that we saw in the first few lectures. Okay, so again, we have reality in the rows and decisions in the columns. And you can see from this, so I'm doing this for the random forest model. You can see from this table that the random forest is doing pretty okay. So then 90 true negatives, 58 true positives, 16 false positives, and 24 false negatives. Okay, so it's okay, it's decent, it's not fantastic. Now let's go ahead and do the same for logistic regression. And you can see that in some ways it's doing better, in some ways it's worse, right? So there are fewer false positives, but there are more false negatives. Okay, and based on what you want, so maybe you care about true positives more, you would say that, okay, then logistic regression is better. But this is, in some sense, this is not, this is not ideal, because now you have like these 4 different numbers and you want some way of combining them again into a single number. Okay, so we'll come back to this story in a little bit, but now we're going to take a deeper look into what classifiers are doing. And essentially, when you open the black box of what the classifier is doing, or you open it slightly to make it into a gray box, you would see that classifiers are all based on using some form of thresholding. Okay, so what does this mean? Right, so let's use the sklearn predict method. Okay, so I'm going to see what my predictions are, my test sets. Right, it's going to give me an array of true false values. Okay, so I'm predicting class 1 or class 0. Now, sklearn methods or sklearn models have these other methods called predict proba. And let's look at what it does. Okay, so it's going to give me an array whose number of rows is the number of samples in the test set, and I have 2 columns. So what are these values? So these are precisely the class probabilities. So for instance, the first row over here is saying that the first sample in my test set has 0.91 probability of being class 0 and a 0.09 probability of being in class 1. All right. And it's a very interesting question to think about, what these probabilities mean. And it turns out to be pretty deep and probably beyond the scope of this class. But if you're interested, you can a keyword that applies in such a setting is calibration. So if you're interested and curious, you can read on Wikipedia about this. Okay, but I am not going to talk about it. I'm going to focus on RC curves. And the important point to note here is that if we focus on the class 1 probability, meaning the second column in this matrix, okay, so I'm going to isolate this now, like this, like so. And I'm going to round it. Then this gives me 1 number for every individual in the test set. Okay, and this number is the class 1 probability. And essentially, when you want to predict what the class is, the default option for sklearn is to threshold this class probability. Right? And the default is to threshold at the 0.5 value, meaning that if the model estimates the class probability of class 1 to be bigger than 0.5, it says that, okay, I think you are class 1. And conversely, if the estimated probability is less than 0.5, the model is going to say that that sample is probably a class 0. And we can actually test this, right? So I wrote this code to test it. So here I have a comparison, a logical comparison, or a pairwise comparison between entries in a vector. The left vector is going to be my class 1 probabilities that I impute using my random forest model. And on the right-hand side, I have this vector, which is simply the class predictions. Okay, NP-all is saying, checking that all the values in this vector are going to be true. Okay, I run this. Oh, it's false. Oh, okay, so what happens? So maybe this should be this. Yeah. Okay, so the threshold is going to be greater than, not greater than equal to. Okay, so good to know, I guess. And I guess the key point here is that 0.5 is an arbitrary threshold. Okay, so it kind of makes sense in some settings, but it may not make sense in other settings. And if you vary the threshold, you're going to get a different confusion matrix. All right, so let's do this. Okay, so now I set the threshold to be 0.25. And when I look at the confusion matrix I get out of it, it looks kind of different from before. All right, so if I compare it to the earlier table, if I remember correctly, now there are a lot more false positives, but fewer false negatives. Okay, so I gained some and I lost some. And you could say, you know, it's sort of debatable whether this is better or worse. In this case, I'll argue that this is worse because there are a lot more false positives, much more so than the reduction in false negatives. Okay, so looking at the confusion matrix is fine. It's even more helpful to do a plot. Okay, so let me run this code and let's take a look at what this plot is doing. All right, so what I'm doing here is plotting the true label. So I'm doing a scatter plot of all the points at my test set with respect to the random forest model. And on the y-axis, I have my true label of the points. On the x-axis, I have the predicted class 1 probability. And I have a typo here. Right, and these are the predictions from the random forest model. And you can see from this that there's a range of predicted class probabilities and the overlap. Okay, so there isn't a clear separation between the two classes, which is why we did not get perfect classification. Okay, and these are the predicted class probabilities. In order to obtain a classifier, we need a threshold, right? And now, depending on how you set the threshold, you're gonna get different classifiers. So now, let's go ahead and remove this comment. So here I'm going to set the threshold to the threshold value that I had before, which is 0.25. And I run this, I see this line here. And what this means is that all the points to the left-hand side of this line are going to be they're going to be given the label 0. And all the points on the right-hand side are going to be given the label 1. So if you were truly class 1 and you land to the left of this line, you would become false negative. Conversely, if you land to the right of this line, you would be a false positive. Now let's do this for a range of values. Okay, and first I need to change some of my typos. Okay, so I put all the code together so that I can change my plot my plotting table just by changing this threshold. Let's start with a threshold of 0. All right, so when the threshold is 0, what happens? My line is here, nothing lies to the left of it. This means that I don't have any false negatives, right? So 0 false negatives. But on the flip side, everything's going to be false positive, right? All of my class 0 samples are going to be false positives. Now, if I change my threshold by a little bit, to 0.2, for instance, and move the line to the right, now not everything's going to be, not all my class 0s are going to be false positives, but at the same time, I'm going to get a few false negatives over here. Okay, and I can keep doing this. I keep shifting the threshold, 0.4, and then you see the trade-off in action again. And ultimately, when I reach the threshold of 1, everything is going to be classified as class 0. So I'm going to have no false positives. But then now in the bottom row, everything is going to be a false negative. Okay, so with all these different numbers for different thresholds, I want a way to aggregate all of this together into a sigma diagram. And the way to do it is through ROC curves. Okay, so to go from what we had before to ROC curves, the first step is to convert values into TPR and FPR, right? This is simply to normalize them. And now we have the range of behaviors that we saw just now, right? So at the threshold of 0, I have everything's going to be, so I'm going to have no false, false negatives, but at the same time, everything's going to be false positive. All right, and then so on and so forth. Now, these are all numbers, and I can plot these in a two-dimensional space where I want the x-axis to represent the FPR and the the y-axis to represent the TPR. Okay, so I can do a scatter plot like so. And I'm going to get 6 points corresponding to these 6 thresholds that I had earlier. Okay, so a threshold of 0 is going to correspond to this point at 1, 1. And the threshold of 1 is going to correspond to a point at the 0, 0 point. Okay, so each point in the scatter plot corresponds to a point on this trade-off curve. And now I can connect the dots, right? So let's try to connect the dots. And this is going to give me some kind of curve. And this curve illustrates the trade-off between TPR and FPR for the fixed model as we choose different thresholds. But something's a little bit fishy. Why did we choose these 6 thresholds? 0, 0.2, 0.4, so on and so forth. It all seems a little bit arbitrary. Okay, so why not, I don't know, why not 0.3, why not 0.36, for instance? And those are perfectly valid thresholds. So in order to have something that is universal and arbitrary, we want to have the maximum number of thresholds. And what the maximum number of thresholds is that we want to have a threshold at the prediction probability for every point, right? So we want to plot the point on this space, on this two-dimensional space, whenever the TPR or FPR changes, and it changes whenever we pass through a certain point, or whenever whenever we shift one point from being classified as positive to being classified as negative. Okay, so we can actually do that. So we can write a function in order to compute these thresholds for every point in the data set, well, in the test set, and there are 200 of these. So it starts to get a little bit complicated. Luckily, sklearn has a function for you to do it, okay? And you can do it, so maybe you've seen this before, maybe not. You can import these 2 functions from the sklearn package. And now let's see how it works. Okay. So sometimes it's good to read the documentation. So this says that it takes 2 inputs and some optional inputs. So we want the true labels, and we also want the scores or the prediction probabilities. And now what's going to give us as output is going to be 3 different objects. It's going to give us a sequence of FPR values. It's going to give us a sequence of TPR values and a sequence of thresholds. Okay, so exactly what we had in the table. I only need the threshold because I'm only going to plot FPR and TPR. So this means that I can drop the last outputs. Okay, so I run this, I get my sequence of FPR and TPR values, and then I can plot it as so. And now we have the ROC curve. All right, so you can see that this curve is a lot more fine-grained, and it gives you the entire trade-off curve. Okay, so visually, this allows us to see how good our model is. Furthermore, we can summarize this diagram into a single number. The number is going to be the area under the curve, right? And sklearn gives you a function in order to just compute this easily. Okay, so I'm going to compute this for both the random forest model and the logistic model. And you can see from this that if you go by the area under the curve, so that's what AUC stands for, it seems that logistic regression is performing better than random forest. Okay, and this is not random. If you run this code several times with different random seeds, it almost seems to be this case. Okay, so why is area under the curve a good number for you to compare different models? Okay, so the reason is you think about what we want for this ROC curve. So what makes a better ROC curve? Okay, so a better ROC curve is where you can have high TPR without high FPR, meaning that we want the curve to be as close as possible to this right angle shape here. Okay, so you want, ideally, under the ideal situation, you want the TPR to go from 0 to 1, without any increase in FPR, right? And then after that, as you slowly increase the threshold, you're not getting any more true positives, right? You're just going to go straight to 1, 1. So that's the ideal situation. So the closer your ROC curve is to that, the better the model is, right? And the closer the curve is to that, the larger the area under the curve. Okay, so this is why the area under the curve is a decent score for comparing different models. Okay, not only that, it gives you an absolute score, right? So we know that the score is always going to be between 0 and 1. 0 is bad. In fact, 0.5 is bad. So 0.5 is what you get when you have a truly random model, and 1 is perfect. Okay, so any score that is sort of like 0.8 and above is kind of okay from my experience, and of course you want it to be higher. Okay, so this gives you an absolute way of evaluating models. Okay, so that's almost the end of the story. I just want to introduce a very related concept called the positional recall curve. Okay, and as with the ROC curve, this also has some implementations in sklearn. Okay, so this function is very similar to, or this curve is very similar to the ROC curve, except that, okay, so I'm going to plot it here for our random forest model, except that there are some changes. Okay, so instead of TPR versus FPR, I'm going to keep TPR, but I'm going to flip it. I'm going to put it on the x-axis, and on the y-axis, I have precision. And what is precision? Precision is simply 1 minus the FDP. Okay, so now instead of comparing two row-wise rates, I'm comparing a row-wise rate with a column-wise rate. And that's going to give me a different trade-off. Okay, so there's still a trade-off, but it's a different kind of trade-off. And sometimes this may be what you care about, because you might care about the FDR or precision, because they are essentially the same thing. And if you read about why people use this compared to the ROC curve, sometimes people talk about the issue of class imbalance. So they say that for when you have class imbalance, so meaning that when your class 1 samples are rare, so maybe only 10% of the samples are class 1, everything else is class 0, then the ROC curve area is kind of optimistic, whereas this the area under the position recall curve is not so. So I actually disagree with that. So I think there should be a fair amount of debate. However, what this PR curve gives you is something else. So this is something that that brings the issue of precision in. And sometimes, there might be some settings where you care about precision more than you care about FPR. In this video, I want to help clarify the connection between hypothesis testing on the one hand and binary classification on the other hand. So let's start with a refresher of what hypothesis testing is. Okay, so in hypothesis testing, we have two hypotheses. We have H0, which denotes the non-hypothesis, and H1, which denotes the alternate hypothesis. So these two hypotheses are both hypotheses about the state of the world. So the world is either in one of two states. Either it is in the 0 state for H0 or is in 1 state for H1. And more precisely, what the state of the world means is really a statistical distribution, or rather a statistical model. Okay, so on H0, we usually have some model for how the world behaves, and on H1, we have a different model. Okay, and sticking with this high-level framework, what happens is that we observe some data X, and X here can be any form of data. It can be a scalar, it can be a vector, it can be a matrix, so some data that you observe. And we want to, our goal is to make a decision. based on X. And the decision can be, is one of two things. So either we accept the null hypothesis H0, or we reject the null hypothesis H0. All right, so this framework is asymmetric. It's asymmetric between the null hypothesis and the alternate hypothesis. And the reason is because of the Neyman Pearson paradigm that you saw in some of the previous videos. Okay. We want to, so essentially, we want to have overwhelming evidence that the null hypothesis is not tenable before we reject it. And some would say that when you reject null hypothesis, you accept the alternate hypothesis. Although there's probably a lot of debate about that. All right, so enough with the abstract framework. So here's a concrete example of hypothesis testing. So this is the example of Gaussian mean testing. All right, so it's a favorite first example. And here, the null hypothesis is that we have data x1. All right, so let's be consistent with the notation and call this Z1 to Zn. And these are random variables that are drawn ID from some Gaussian, say with mean 0 and variance 1. And under the alternate hypothesis, the same Z1 and Zn are drawn ID from some other Gaussian, let's say Gaussian and mean 2. Now, what's our data? Our data, of course, is going to comprise of these numbers Z1 to Zn, all right? Okay, so the entire vector of these numbers is our data X. And now our decision, our goal is to accept H0 or reject H0. Okay, and how do you do this? Well, you know what the distribution is of the two Gaussians. Okay, so this is going to be the distribution under the norm. And here's the distribution under the alternate hypothesis, right? And we want to see where our data lies. Okay, so if our data is sort of like this, centered around the origin, then it seems like the null hypothesis is more likely, so we accept it, and we do not reject. Okay, so this is an easy example of hypothesis testing. Now let's try to relate this to classification. So what happens for classification? So let's talk about image classification, since that is, again, an easy first example. So you start with some class, all right? So let's say cattle dog, and the class is going to give you some image. So this image is your data. You put the data into a classifier. And okay, let's call this image X. And out from the classifier, you have some predicted class, right? Which is data cattle. And now you can compare your predicted class Y hat against the true class Y. Okay. So that's how classification works. And let's try to see how hypothesis testing fits into this framework. So what happens in hypothesis testing? So you have either H0 or H1. This model of the world is going to give you some data, right? Okay, and maybe I should be a bit more careful with the squares and circles as well. So let's make this a circle. You feed the data into some decision algorithm. And then out from the decision algorithm, you get a decision, right? And the decision can either be accept or reject. Now, how is this classification? Well, it has to do with the indices, right? So if we accept H0, this is sort of saying that I estimate the index of the hypothesis to be 0, plus 0. And then if I reject H0, it means that I predict the class of, well, I predict the index of the hypothesis to be 1, right? So this is just playing with the language. Okay, and in this case, we can compare the predicted index with the true index for the hypothesis. Okay, and this means that we can say either we got the class right or we got the class wrong. Okay, so this is, now you see from these two diagrams that hypothesis class testing is very, if you massage terminology a little bit, it's exactly the same as classification. However, there's going to be some differences that we will see later. And these differences are a little bit subtle. But first, I'm going to talk a bit about p-values, right? And p-values comes from expanding this box over here that at the moment is just a black box, right? So we have a black box decision algorithm. So how does the decision algorithm work for hypothesis testing? So essentially, when we expand the black box, okay, so let's try to expand it. So what's happening here is that we're always going to compute the test statistic T of x. And then the decision is the algorithm is going to be, we see if T of x lies in some reject region, R, then we reject, and otherwise we accept. All right, so this is how this decision algorithm always works. And using p-values, it's just a special form of test statistic. All right. So it's choice of test statistic so that under the null, you have a uniform distribution over the interval 0 to 1. All right. And as you've seen from lecture, any test statistic can be converted into p-value. Or rather, any test statistic that is real valued can be converted into p-value. Okay. So p-values are just a specific test statistic, and test statistics are objects that lie at the heart of any decision algorithm. Okay, so now where are the problems in this comparison of binary classification and hypothesis testing? Okay, so the problem lies when you start to consider multiple hypothesis testing. Okay, so under multiple hypothesis testing, you have multiple hypotheses. And I guess the analog of that in classification is where you have many samples, which is the standard setting. Okay, so going back to this diagram here, you don't just have one class and one image, right? You instead will have like many samples. Each one of them is going to generate an image. And then every image you put into the classifier. and the classifier is going to give you a label for every image. All right, and the standard setting, at least in theory, just our standard assumptions for classification is that these image class tuples are always drawn ID from some distribution D, right? So this is the standard machine learning assumption. Now, what happens for multiple hypothesis testing? Okay, so here's some hypothesis. So the indexing here is going to be a little bit strange. So let's plot this HAI. Well, I don't want to use, okay, my bad. Let's change this to H1I, H2I, H3I, so on and so forth. And the i's here, okay, so I'm going to say that the i's are either going to be 0. They're either going to be 0 or 1. And each hypothesis is going to give us some data, x1, x2, x3. We plug this into some decision-making algorithm. And then it's going to spit out decisions. All right. So aside the reject, let's also call these white hats, so on and so forth. Okay. However, now we no longer assume that our test statistics are independent. Okay. So the randomness structure in multiple hypothesis testing is different from that in binary classification. So in other words, we no longer assume that the data that we have here are independent. Okay. In fact, we no longer assume that they are even identically distributed. Okay, so they could have different distributions. You can have wholly different test statistics, and yet you can consider all these very diverse heterogeneous hypotheses in the same framework. Okay, so why will your data that goes into the decision algorithm not be independent? Well, say you have the exact same data set and you want to see, for instance, you have some health data on people and you want to see what health characteristic causes cancer, for instance. You can have like 100 different hypotheses about that, right? So does high blood pressure cause cancer? Does smoking cause cancer, etc.? And all of them use the same data set. So the X is exactly the same for all of these hypotheses. Okay, but yet at the same time, you can fit all of these different hypotheses into the same framework. Okay, so I hope this video helps you clarify in your mind the connection between binary classification on the one hand and hypothesis testing on the other hand, and also explain some of the subtle differences between them.